University of Delhi. Feel honored to welcome our esteemed speaker, Dr. Arna Banerjee, our respected Principal Sir, Professor Rajiv Agarwal, Vice Principal Sir, Professor Kamal Kumar Gupta, IQAC Coordinator, Dr. Aditya Saxena Sir, DBT Star College Scheme Coordinator, Dr. Indrakant Singh Sir, respected faculty members from our college and other colleges of the university, researchers, and keen students on this auspicious occasion of the second day of International Lecture Series on Recent Advances in Physics. It's my pleasure. It's my pleasure to welcome our eminent speaker, Dr. Arnab Banerjee, Department of Physics, Pahjo University, West Lafayette, and visiting scientist, Quantum Computing Institute, Oak Ridge National Laboratory, USA. I thank Dr. Arnab that he graced us to share his knowledge and enhance our mental rights with his wonderful talk. This lecture series will be a great platform for the researchers and students from all over the world to understand the recent work going in the field of physics and to interact and share their innovative ideas with the renowned speakers. I really do hope that our students make the best out of it. Going along, I would like to invite our respected Vice Principal, Sir, Professor Kamal Kumar Gupta, to speak a few inspiring words. Over to you, sir.
Very warm and bright good morning to one and all present here. It's my proud pleasure to welcome today's keynote speaker, Dr. Arnab Banerjee. Welcome you, sir. I take an opportunity to welcome our respected principal, Professor Rajiv Agarwal, IQAC coordinator, Dr. Aditya Saxena, DBT Star College coordinator, Dr. Indrakant Singh, all the faculty members of Deshbandhu College, other college, India and abroad, and of course, all the participants, including all the students. This event, International Lecture Series, organized by Physics Department, in fact, is really a wonderful. Today, it's the second day. And yesterday, again, that was a wonderful interaction of the students and the keynote speaker. So today's speaker is Dr. Arnab Banerjee, who is scientist at Department of Physics and Astrophysics, University of Purdue, Lafayette, and also the visiting scientist. Students, this is a golden opportunity for you to interact with internationally acclaimed scientists. And I congratulate Physics Department for organizing such a wonderful event. I congratulate especially the teacher in charge, Dr. Kakuli Behra, then all the young faculty members who are always instrumental in making such dream a reality. Yes, I say it's really a dream, and that's why we are known, Delhi University is known, Deshbandhu College is known to be in touch with internationally known personalities. Thank you, Monica, once again. Welcome once again, and now over to you.
Thank you, sir, for sharing your words of wisdom with all of us. Now, without any further delay, I would like to call our teacher in charge, Department of Physics, Dr. Kakuli Behra ma'am, to introduce our utmost speaker and begin the most awaited event of the day. Over to you, ma'am.
Thank you, Dr. Monica Sharma. Good morning to all of you in India and good evening to Dr. Arnab Banerjee. I, Dr. Kakuli Behra, on behalf of Physics Department, Deshbandhu College, University of Delhi, welcome our Principal Sir, Professor Rajiv Agarwal, Vice Principal Sir, Professor Kamal Gupta, distinguished speaker, Dr. Arnab Banerjee, IQAC Coordinator, Dr. Aditya Saxena, and DBT Star College Scheme Coordinator, Dr. Indrakant Singh, all faculty members of India and abroad as well, all the participants, and all the students in this international lecture series on the recent advances in physics. Today is the second day, and today's topic is quantum spin liquids, novel platforms for emergent quasi-particles. It's a great pleasure for me to introduce Dr. Arna Banerjee to all of you with his brief academic record. Dr. Arna Banerjee is currently working as an assistant professor in the Department of Physics and Astronomy, Purdue University, West Lafayette, and he is also the visiting scientist in Quantum Computing Institute, Oak Ridge National Laboratory. He received his MS and PhD degrees from University of Chicago, USA. He worked on quantum and classical phase transitions revealed using transport and X-ray techniques for his PhD degree under the supervision of Professor Thomas Rosenbaum, University of Chicago. He is actively working with ORNL, IBM, D-Wave, and Fujitsu to develop new quantum algorithms for materials. He is also working on developing new measurements and techniques for neutron scattering, phonon, and magnon density of states measurements. He is also working to develop program on quantum measurements, neutron scattering, quantum materials, and quantum algorithms. The awards and the honors which he received, first is the Reviewer of the Year Award by Journal of Physics Condensed Matter Institute of Physics in the year 2019. Second is Postdoctoral Award from Materials Research Society, MRS, in 2018. Third is the Top 100 Science Achievements of the Year Award by Discover Magazine in 2016. Fourth is the Director's Award from Oak Ridge National Laboratory in 2016. Fifth is the Research Excellence Award for Team Research, UT Bataley Memorial Foundation in 2016. Sixth is the Subramaniam Chandrasekhar Fellowship from University of Chicago during 2006 to 2009. Seventh is the H.N. Bose Award from Department of Physics, IIT Kharagpur in 2006. Eighth is the Institute Silver Medal from IIT Kharagpur in 2006. Ninth is the Jagdish Chandra Bose National Science Talent Fellowship from Government of West Bengal from 2001 to 2005. 10th is the Indian Academy of Sciences Student Fellowship from Government of India during 2004. And 11th is the Undergraduate Research Award from Shah Institute of Nuclear Physics, India during 2002 to 2004. He has 39 research publications in various journals like Physical Review Letters, Physical Review B, Nature, Nature Physics, Nature Communications, and so on, with an H index of 25. He has a brilliant academic record. Now it's my great honor to welcome Dr. Banerjee for his talk on quantum spin liquids, novel platforms for emergent quasi-particles. Welcome, sir. Over to Dr. Arnab Banerjee, sir.
Thank you, Kakuli, and thank you, Monica, and thank you, Kamal Gupta. Can you hear me? It is my honor to be here and present this talk to this audience. And so I will share my screen. I just want to make sure that it shares correctly. And then I will slide share. So can you see my slides?
Yes, sir, it is visible.
Fantastic. So once again, it is my honor to be here, and good morning to everybody in India. And it is 11 o'clock at night here. And it is my pleasure to be in my bedroom right now, basically presenting this talk to you. And I really look forward to the discussion. Today, I will be speaking about novel platforms for emergent quasi-particles in quantum spin liquids, and a work which has been done in collaboration with Oak Ridge National Laboratory, Purdue University, Max Planck Institute, University of Cambridge, and many other places. So as an outline for my talk, I will be introducing you to this concept of what exactly is a quantum spin liquid. And I will also introduce you to Kitaev-type quantum spin liquids, on which I have actually researched quite a bit. I'll be introducing you to neutron scattering, the visualization of quantum spin liquid behavior in alpha ruthenium trichloride, a material on which I have worked a lot, challenges towards devices on topological quantum computation, and then on programming of spin states on quantum machines. So the main idea that I want you to get out of the talk is that spin liquids is a new state of quantum matter which shows stable quasi-particles and emergent chiral phases. And I will come to what exactly that means. I will be talking about, so alpha ruthenium trichloride is a material which shows proximate Kitaev spin liquid state, and we see evidence of fractionalized fermions called Marina Fermions, and it actually provides us with a new paradigm towards topological quantum computation. And so that I don't run out of time, I want to acknowledge all the people whom I've been working with, especially Stephen Nagler and Alan Tennant at Oak Ridge National Laboratory at Princeton, with Nai-Fong Ong's group at Max Planck Institute, Roger Schmersner, and then a lot of folks at UC Berkeley, Los Alamos National Lab, Microsoft, and Caltech. And the work has been supported by the Department of Energy, Basic Energy Sciences. So when we talk about spins, what exactly is a spin? So when we talk about spin in this talk, what we actually mean is the unpaired spin half moment of an electron. So let's say that you have a material, and in that material you have the orbitals, and the orbitals fill up because of Hund's rule, and then you have one unpaired electron in the outermost orbital, so that will lead to a spin half moment. That's the spin half moment that we are talking about, and that's what I will refer to as a spin. There is another source of spin that you can get, that is the orbital motion of the electron across the orbital motion of the electron around the nucleus also produces an L, and so the total spin eigenfunction, the J, is L plus S. So if you think about it, so what I mean by a spin is basically this unpaired electrons, which you can think of as like a tiny bar magnet of net spin half. So I will go into this new state of matter, which we are talking about is a quantum spin liquid. So if you search quantum spin liquids in Google, what you will find is this picture. Now, it's actually a matrix of spins floating on a liquid. I don't like that picture. And the reason I don't like that picture is that that picture is not quite correct, because here as if it seems that the spins basically move all over the place like ducks on a pond. But that's not what happens in the kind of materials we are talking about. What we are really talking about is that the spins are actually situated at the lattice point. So in a material, all the elements are actually sitting in their own respective lattice positions, and those respective lattice positions carry the spins. And it is the direction the spin points which really determines whether it will be a spin liquid or not. So in some ways, instead of this picture, it is more like a Buddhist prayer wheel, which are situated in their own place, but can rotate in different directions by being in their place, is what this situation really resembles. So what we mean technically is that we have non-itinerant local spins. So the spins cannot move from one place to the other. So what has this concept of spin given us so far? So there are many spin phases of matter that we know, but the biggest spin phase of matter that we know is the ferromagnet. And ferromagnet, what we know is that if you, let's say, have a lot of spins in a material, and then you make one spin point up, what it really does is that the interactions makes the next spin point up as well, the next spin point up as well, and all the spins eventually point in one same direction, which is up. And that is what happens because of this interaction, which is called an exchange interaction, where the energy is minimized when all the spins point up. But this is, but there is a very beautiful concept here, which is if you now take one spin and try to make it point down, this force is basically going to come and make the spin point up once again. So as if you cannot really make the system go wrong, the spin always wants to point up. And that is exactly this concept of protection, which has enabled us to have things like magnetic memories and MRAMs and memory devices, something that we use in everyday life. What really is happening there is that there is an energy barrier which prevents the upspin from becoming a downspin. And this energy barrier is what protects your memory. It is the reason why your memory, you can store your memory in a flash drive and it just does not disappear over a long period of time. And that's the concept of protection that is extremely important and is extremely powerful. And what we will come to is a concept of topological protection in this talk and how we can get from spin states. Now, this is just one kind of spin state that we can get in a material, but in nature, there are so many other kinds of spin states. And to be honest, we are really not using them as devices so much. So there is a huge amount of promised land because of all these new states of matter that we can use to make new kinds of devices. And some examples would be topological phases like skyrmions, which basically have very exotic spin structure like I have drawn here. You can get new emergent phases of matter, such as spin ices and spin glass. And the whether a material is a spin ice or spin glass depends on how exactly the spin coordinations are between the various neighbors. And in these spin ices, you can get very new kinds of phenomena like Dirac strings. You can get magnetic monopoles, which is impossible in real life, but you can get emergent magnetic monopoles. And then, of course, you can get emergent defects and domain walls, which you can use to also store information, to also process information. And so discovery of these new magnetic phases of matter is very important as it will lead to new applications in spintronics. And my talk kind of really addresses that. But it's not only just static phases of matter. There are many dynamic spin phases of matter that are also there. So what I described in the previous slide is static phases of matter where spins really are not moving. But you can also get new states when the spins are moving around and the spins basically are dancing as if. And depending on what kind of patterns they produce when they are moving around can also produce new states of matter. And when that happens, you get various new kinds of states, such as spin liquids, orbital liquids. You can get liquid spin crystals. You can get spin superfluidity, a whole gamut of spin phases of matter that one can use. So that actually tells you what is the level of promise that we can get from these kind of systems. And to elaborate it a little bit further, and as I mentioned, that we can get to things like spin ice, which I will not cover in this talk. We can get to things like valence bond solids, and what that is, I will explain later, but quite a lot of work has been done on that. And then you can also get to quantum spin liquids, where you basically get long-range entanglement, but short-range correlation. Again, what that is, I will come to in a bit. But here you can get this topological protection is the concept that I just told you about. So what exactly is a spin liquid? So we know of phases of matter. We know of phases of matter, solid, liquid, gas. So if you decrease the temperature of a system of atoms, what you get is that when there is a lot of energy in the system, then you get a gas where things just look like random. And then when you cool it down below liquefaction temperature, what happens is that these gas molecules basically start forming bonds in dynamic fashion, and that's when you get to this liquid state. And then when you cool it down even further, what happens is that everything just sits together rigidly, and what you get is a solid, which is extremely hard. And that's exactly what you also get in spin states in these solids, where, but here it's the direction of the spins, as I mentioned, which is what is doing the trick for you. So what happens is that the spins can face any direction, and if the spin directions are all random, then what you get is a paramagnet, which is exactly like a spin gas. Here you have fully disordered motions. And then what happens when you reduce the temperature after that is that you can get to a spin liquid like or nematic like state where the spin motions start to get kind of, I should say, slightly arrested, and things become a little bit more, should I say, slow. Things are not quite as random as you would get in a spin gas. And then if you cool the system further, so that would be a kind of a critical state. And then when you cool this thing further, you will get to something like a spin solid, where all the spins are kind of pointing in one very particular directions. And an example would be a ferromagnet, an antiferromagnet, a ferrimagnet, so on and so forth. However, a quantum spin liquid is different, because even if there is a strong interaction in between the spins, for some weird reason, which I will come to later, for some weird reason, the spins really cannot arrange themselves like a ferromagnet or an antiferromagnet. They keep on fluctuating even at zero temperature. When you have cooled it all the way down, you would have expected a solid state, but that's not what you get, as if you get a liquid state even when you have temperature of 0 Kelvin. And that is happening because of quantum zero-point motions or quantum fluctuations. And when that happens, you get long-range entanglement, and you get this enigmatic state called a quantum spin liquid. So what exactly is a quantum spin liquid? A quantum spin liquid is a state where all the spin motions are seemingly disordered, but there is some orderliness in, and they are disordered because of Heisenberg uncertainty, really. But there is seemingly an orderliness in that. What is really happening in a quantum spin liquid is that you have long-range entanglement, and all the spins are entangled with each other, just as you have in a quantum dimer state, and I will come to that again. But the directions are all disordered. That is why you get highly degenerate ground states. But somehow, because you have strong interaction in between the spins, the motions are ordered. So how to think about that? Think about water. In water, it's a liquid. At any snapshot of time, it seems that all the water molecules are just randomly moving around, as if we're just like a disorder. But if you throw a stone on the top of the water, you start forming ripples. You start forming waves. Those are very ordered motions. It's exactly like that what happens in a spin liquid. Even though all the spin directions appears to be disordered, if you perturb the spin liquid, if you kind of excite the spin liquid, you will see that you are also forming these wave-like patterns. You are forming these vortices, anti-vortices, just like you see in water. So you start to see this topological phenomena. You start to see very ordered motions in a spin liquid, something that you don't see in a paramagnet. And because of these ordered motions, what you can also generate are these quasi particles, which happen because the spin bonds are breaking and unbreaking and breaking and unbreaking. It can break and unbreak in several kinds of patterns. And because of these patterns, what you get are these quasi particles. And since it's really the motions which is doing the magic for you, you need probes that can look at motions to really understand a quantum spin liquid. So you need dynamic probes. So you would see the signatures in spectroscopy instead of seeing the signatures in any static probe. So, and that is actually very important. And then the dynamics, as I mentioned, are often very topological in nature. So you would see things like vortices, quasi-particles, fractionalization, all of which show long-range entanglement. So if we look at the history of entangled quantum states of matter, so it started really with P.W. Anderson back in 1970s and 1980s, and it was then perfected by Duncan Holden in 1983. And Duncan Holden, as you know, got the Nobel Prize a couple of years ago, along with Kosterlitz and Paulus, for topological states of matter. So what he had proposed is that a two-spin entangled state is actually a building block. It's the smallest unit of an entangled system, a quantum entangled system, because you see that as soon as you have two spins which are completely entangled, what they form is a completely new state, which is called the dimer pair. So you get something called a triplet gap. You cannot really define a triplet gap with just one spin. You need to have two spins together to define this concept of a triplet gap. And then you get this a state which is a singlet, which, as you see, is a completely entangled state between two spins. You cannot really separate one spin here. There is no way to separate one spin here. And then you get this triplet state, which is also a completely entangled state of these two spins. And then those are separated by a spin gap. It is protected by a spin gap, which is the triplet gap. So when now you consider, let's say, state which is made up of this small building blocks of dimers. You take one dimer and put the next dimer beside it, put the next dimer beside it, you make it into a chain. What happens is that all the dimers in this chain are actually protected by this spin gap, and you basically get a protected spin chain. How does the excitations of that look? The excitations of this does not look like your normal magnons or normal bosonic excitations. They don't look like that. They look like something we call spin-ons. What is happening here is that the entire state is changing from s is equal to 0 to an s is equal to 1. And it is this s is equal to 1 excitations that will propagate from one spin bond to the other. So that is exactly what is a spin-on, and it's very different from a magnon, which is basically just a simple dancing of the spins. So, and as you see that in order to excite a spin-on, you have to basically go across the spin gap. So unless you give that much energy into the system, you cannot really surpass that gap. And so the system is kind of protected by that gap. And so that is how this concept of protection comes. And the great thing is that you can actually see the signature of such spin-ons in real experiments, such as neutron scattering, thermal transport, specific heat. And there are many such papers. And you can also kind of make an artist's visualization of how that might look in real life, material, how the spin-ons can propagate. But what is more exciting is that just this simple model, it already embodies the concept of topology and topological protection. If you have a gapped s is equal to 1 state, which I just described in the previous slide, what you get, and then you kind of truncate that chain on two sides, what you get at the ends are basically emergent s is equal to half states. This spin half states are completely protected. These are the quasi particles, which are fractional in nature. So if you have a spin 1 system, you get emergent s is equal to half edge modes in such a gap system. And such a state is the famous AKLP state, that like the Takashi state. Sorry for the tongue twister, but that's the famous state that you get. And that is kind of the main concept that embodies how people have been trying to go into this Marina spin chains, and you would have this Marina quasi-particles which are trapped at the end of the spin chains or edge modes. This is basically the seed of the understanding, the seed of that understanding. So this is all in 1D. This is all in 1D. Now let's come to 2 dimensions. So in 2 dimensions, let's come to this concept of an RVB. What we get is an RVB spin liquid. So in 2 dimensions, you can consider a simple motif of a triangle. And consider that you have an antiferromagnetic interaction between the 3 legs of this triangle. Now, something very weird happens. what happens is that if you have antiferromagnetism, then at any point of time, only one set of bonds can satisfy and the other set of bonds cannot satisfy. If this pair forms an antiferromagnet, then this cannot form an antiferromagnet, or that cannot form an antiferromagnet. If this spin points up, then this bond is unsatisfied. If this spin points down, then this bond is unsatisfied, which means that at any point in time, in this simple motif, you cannot satisfy all the bonds at the same time. You can only satisfy two of the bonds, and one bond will remain unsatisfied for you. Sorry, one bond will be satisfied and two bonds will remain unsatisfied for you. So what that means, and there are three ways in which you can do that. Why? Because you can make this bond unsatisfied, or this bond unsatisfied, or the third bond unsatisfied. So you get three choices. And all these three choices basically are degenerate in energy. They all have the same energy. Such a state is actually called a frustrated state. Why? Because it is the concept of frustration. Frustration means that you are not being able to satisfy all the conditions at the same time. And this is exactly what that phenomena is. And what you see is that as soon as you have magnetic frustration, the satisfied bond is called the dimer covering. And the dimer covering can now, all of these states have the same energy, but now the dimer covering can move from one bond to the other without any loss of energy, because all these states have the same energy. And as you see that as soon as you get to that, you have two ways in which this can happen, in a left-hand chiral way or a right-hand chiral way. So you see that you get the concept of chirality or vortex states automatically from just such a simple concept of a triangular lattice. Now let's consider the state, which is basically an extrapolation of this triangular lattice. You take this triangular lattice and then you extrapolate into a much bigger lattice, like a big triangular lattice with many triangles. Such an example would be a triangular lattice or a Kagome lattice, for those who know what Kagome lattice is. So it's basically all these triangles kind of join together. That's a lattice made of triangles. And what happens is that all the triangles are in this frustrated state. And if all these triangles are in this frustrated state, you basically get a superposition of many such solutions, where in every solution you basically satisfy a different set of dimers. And so such a state is called the resonant valence bond state. A simple concept of resonant valence bond state is something that many people have learned for example, in benzene ring, where you basically have a resonant valence bond of 6 bonds. And that is exactly the kind of state that you have here. It is the magnetic analog of a resonant valence bond state, where you get a superposition, entangled superposition of all the states. And as soon as that happens, what you realize is that it really doesn't take any energy go from this state to this state to this state to this state, but all the states are different, which actually gives you an enormous amount of potential to move the bonds around, to move the quasi-particles around, to move the spins around, to break the bond, to make a bond, to break another bond, to make another bond. And you can do that in various patterns of your choice if you can control the material. And that is how these kind of quantum spin liquids start to become breeding grounds for quasi-particles, newer kind of quasi-particle surface cones and fault-tolerant behavior. For example, you can actually encode something called a toric code model into a square lattice quantum spin liquid, where you can actually get two kinds of quasi-particles, the E-type and the M-type, which is like an electric type and the magnetic type of quasi-particles. And then what you can do is that you can basically move these quasi-particles all over the place just by breaking some bonds and making some bonds. And it's very pliable. And secondly, when you can do that, what you can see is that you can take one quasi-particle and you can braid it across. You can form knots, you can form loops, and that is how you can very quickly get to the concept of topology and how you can get newer kinds of topological states in this quantum spin liquids. And that is basically how we think of this state. So there are several experimental platforms for quantum spin liquids. For example, we can have, as I just mentioned, you can get this triangular frustrated state, and you can make a Kagome lattice out of it. This is an example of a Kagome lattice, and there are many examples in literature, Herbert Schmidt being the most famous of that. And then you also get calcium chromate, and there are probably 12 or 15 such materials which exist right now, where you have this concept of geometric frustration, where all the spins are not satisfied at the same time. You can also get another kind of frustration called an exchange frustration or a bond-dependent frustration, something which I will get to. In pyrochlore lattices, you can get something like a mixed frustration, which is a mixture of both geometric and exchange frustration. And then you can basically make a network of like metal organic frameworks or the Shastri-Sunderland model, where you can essentially get frustration as well. So there are several paths you can get to a quantum spin liquid state. And all kinds of quantum spin liquid states, depending on how you make them and what their geometry is, conforms to a certain kinds of topological features. And that actually gives rise to certain kinds of topological classes, such as the gapped Z2, the gapless Z2, the U1 Dirac type, the spin-on Fermi surface type. So there are several kinds of topological classes. And in each type of topological class, you get a different type of quasi-particle. For example, in gap Z2, you get anyons, and in gapless Z2, you get magnetic monopoles. In Dirac spin liquids, you get Dirac fermions and spin metals. You get a zoo of new types of quasi-particles. And I am not going into detail of what all of these are. And a great review article where all of these are described is the review article by XG1. It's the reviews of modern physics, this paper. But the main point that I want you to get from this slide is that each kind of topology that you get from these quantum spin liquid states has its own characteristic dynamics, and each produce a different kind of quasi-particle. And there is a lot of research which is going on right now to search for non-abelian quasi-particles. And you can get an understanding of what these quasi-particles are by studying the dynamics of the materials which host this kind of topological classes. So that's what we do. How do we measure that in real life? Well, so we only have a few tools, should I say, to measure it. And the biggest tool that we have is the dynamic spin-spin correlation. So basically, what we can measure using many techniques is the Fourier transform of the dynamic two-spin correlation, which is measured by neutron scattering using inelastic X-ray scattering, Raman spectroscopy, and MR terahertz. But you can also see the drawback here is that there is no real way we could measure some exotic type of phenomena like multi-spin correlators, loop operators, vortex operators, entanglement entropy, GHZ states. There is really no way to measure those yet. And I think that actually produces where new research needs to happen is to see how we can measure this. How can we do experiments that can measure this? Anyways, neutron scattering is actually a great way to measure the two-spin correlation. And how does it work? So if you have an incident neutron that hits your sample and you then get an exiting neutron, the incident neutron has an incident energy I and an incident momentum Ki, and it exits with an exiting energy F and an exiting momentum Kf. And when that happens, because the sample has certain allowed energy levels, the neutron basically loses a certain amount of energy and a certain amount of momentum. And you can exactly go to a neutron scattering beamline or an experimental setup, and you can measure that directly. Now, neutrons have two different properties. Neutrons have a mass. Since neutrons have a mass, it has a de Broglie wavelength. So using that de Broglie wavelength, you can actually look at the atomic correlations, because if it has a de Broglie wavelength, that means that it has a wave nature. Neutron has both a particle nature and a wave nature. you can use the wave nature of the neutron to look at where your atoms are sitting and how your atoms are moving. But importantly, neutrons also have a spin moment. It has a spin half moment. And the spin half moment can interact with the spins in your system, and you can just get a spin-dependent scattering. So there are two scattering mechanisms that neutrons give you. One is the spin-dependent scattering, and one is the spin-independent scattering. The spin-independent scattering tells you the structure of the material and the phonons, while the spin-dependent scattering gives you the spin structure of the material, the spinons, the magnons, and all the phenomena that I'm talking about here. So, and the beautiful part is that there is this factor called the neutron scattering form factor, which helps you to separate both of these effects. And this dynamic scattering cross-section is basically the Fourier transform of the spin-spin correlation. So if I look at the total spin-spin correlation, that's between two spins sitting, one sitting at this position alpha, and the second spin sitting at this position beta, this is the entire spin-spin structure factor. It looks like a very scary equation, but let me break it down for you. So in the beginning is some boring constants. I mean, it just comes from the interaction term of the neutrons with the spins. Then there is the magnetic form factor. And as I mentioned, this magnetic form factor is what really allows you to separate a magnetic scattering from a non-magnetic scattering. The third term is basically a selection rule, which says that only perpendicular components of the spin scatter. And this is a very, very important term because it allows you to figure out from the scattering phenomena what is the directions the spins are pointing in your material and what is the directions your spins are fluctuating in your material. You can figure that out. But the most important term is the Fourier transform of the spin-spin correlation function, which is what we get from the experiments that we do. So most of the experiments that I will describe here has been done at this Polish neutron source at the Oak Ridge National Laboratory in Tennessee, which is a beautiful, beautiful facility sitting in the Appalachian Mountains, just beside Smoky Mountains. And it has a front-end LINAC followed by an accumulator ring, and then it has a mercury target where you hit a proton almost at the speed of light. And when you do that, mercury is a neutron-rich material, so that basically throws out neutrons in all directions. There are 18 end stations and 24 different instruments that capture those neutrons, and you can take those neutrons in those instruments and you can make them impinge on your material, and that's how you do these experiments. So this is how a typical experiment end station looks, an experimental end station. The neutron comes, and this is the size of a man, and this is how big this system is, this instrument is. Your cryostat sits with your sample in a vacuum chamber right here. This is a staircase. You go down here. There is a lot of shielding material here because, as you know, that these neutrons are fast and it can make everything radioactive around you. So you have to shield everything quite a bit. There is a huge vacuum drum, and beyond that vacuum drum, you basically have your helium-3 detectors, and this whole vacuum drum is maintained at a very high vacuum with huge vacuum pumps. And what happens is that an incident neutron with incident energy Ki hits your sample, which sits right here. It goes and hits the detectors with a final momentum Kf. From looking at Ki minus Kf, so from where the neutron hits, you get the momentum. And from when the neutron hits, you can get the energy. So that is why it is called the time of flight spectroscopy. Because it's the time of flight, the time the neutron takes to hit your detectors is what gives you the energy of the absorption spectrum. Now, of course, the detector is basically a 2D detector, and you don't get the 3D information from it. Your sample is 3D, you need the 3D information, but in order to get the 3D information, you do exactly what you do like a tomography. Like in a tomography, what you do is that you impinge your sample with a beam, and then you slowly rotate your sample, and then you construct your entire 3D picture. That is exactly what we do here. We keep on rotating our sample as the neutron hits, and then we slowly rotate it, take a frame, slowly rotate it, take a frame, slowly rotate it, take another frame, and then we we almost get 2 terabytes of data. And then we join these 2 terabytes of data into one single file where we can get all the information together. And that's how we can get the entire reciprocal space map in both space and time, in energy and momentum. And there it contains all the information of the phonons, the magnons, the spinons, and everything. So looking at 2 terabytes of data is challenging, but that is something that as a neutron scientist we are trained to do, is where to look for the information. So conventional magnets, what does the spectrum look for conventional magnets? If you look at the dispersion in conventional magnets, which has magnons, if this is energy, this is the momentum axis, what you get are these cone-like features. And if you just make a cut across one of these cones, you get such a parabola type shape. And this is how the dispersion looks in the plane QK, So as you see that, you basically get these circles, which is like you are cutting right here. If you are cutting one slice right here, you will get this cone. So as you go up in energy, you see that these cones become bigger and smaller. So this is exactly how things look for a conventional magnet, but that is not how things look for the spin-ons. And if you have spin-ons, what happens is that you get really fluctuating moment. And if you get a fluctuating moment, what you get is are states which are very broad in energy. And the reason is that if you have fluctuating moment, means that you have states which have very small lifetime. And if you have states with smaller lifetime, that will be broader in energy, while states with longer lifetime will be shorter in energy. Secondly, if you have states which are have long correlation length, will have very sharp momentum space features. States which are short will have short correlation length, have broad momentum space features. And so what we see is that when we have fractionalization, what we get is this broad energy momentum signatures. And that's exactly how we can get to spin-ons. And what happens is that, let's say that you have this Heisenberg antiferromagnetic chain where you can create an S is equal to 1 spin-on, which let's say fractionalizes into 2 spin-half solitons. You can calculate the spectrum directly using the beta ansatz. And this is momentum axis, and this is the energy axis. You see that you get this broad bunch of states is what you can predict. And that is exactly what has been measured in real materials which show this kind of phenomena. You see this broad bunch of states. And what we are, and the signature of this broad bunch of states, it's not a random broad signature. It has a very specific energy momentum signature, these broad states. And that's what you can really calculate and you can map it. And that's exactly the signature that we are looking for in quantum spin liquids, as well as was shown in this Nature paper by the MIT group. And in resonant valence bond systems like this triangular lattice, antiferromagnet, ytterbium magnesium gallium oxide, people have shown that you can see this kind of large, broad, blobby states in both energy and momentum, which is actually one of the signatures of quantum spin liquid, or spin liquid, quantum or not, spin liquid, as we mentioned. So now let's come to this concept of a K-type quantum spin liquid, and I have to go faster a little bit. How much time do I have?
Dr. Arna Banerjee, you take your time.
Okay. All right. So, so let's come to this concept of a K-type quantum spin liquid. In a K-type quantum spin liquid, what we have is this Y kind of a motif. This is a Y where each leg of Y has a different Ising interaction. And this is the resulting Hamiltonian you get. So this leg of Y has this JXX interaction along the X direction. This leg of Y has a JYY interaction along the Y direction. And this leg of Y has a JZZ interaction along the Z direction. So you see that all these 3 directions point in 3 different Ising directions. What happens to the spin which sits right in the middle? The red term bonds try to pull that spin in one direction. The blue bonds want to pull the spin in a second direction, the gray bonds want to pull the spin in a third direction. So that spin is completely frustrated. That spin is completely confused, let's say. And that is what gives rise to this bond-dependent frustration, because this gives, as you see that this happens because three bonds basically have three very different directions, which makes the spin frustrated. You take this Y motif and then you extrapolate it to a honeycomb lattice. As you see that the honeycomb lattice is basically constructed of a Y, an inverted Y, a Y, an inverted Y. It's basically a net of Ys and inverted Ys. And all the spins here are frustrated because of this reason. And in such a model, the ground state is actually a quantum spin liquid, as was solved by Alexei Kitaev back in 2006. And you get the solution basically is a superposition of many such states, degenerate states, where for every superposition of every state, you see that sometimes these bonds are satisfied, sometimes some other bonds are satisfied. So you basically get a superposition of all the states. And that's the state of matter that you get in this kind of a quantum spin liquid. So you get a highly degenerate state. But this is an Ising, these are all Ising dimers, by the way. And this is basically a system which was solved by Alexei Kitaev back in 2006 in his seminal paper, which is this paper right here, when he was at Caltech. He's still at Caltech, but he was also double timing at Microsoft Station Q at that point. So what he was able to show that if you have the spins on the 6 corners of this honeycomb, you take those spins and you construct a product state of the 6 spins, and that product is actually a conserved quantity +1 or -1. That means that the system has an emergent Z2 symmetry. When you have an emergent Z2 symmetry, what he was able to do is that he was able to rewrite this entire Hamiltonian. Given this Z2 symmetry, he was able to write this entire Hamiltonian in the basis of just Marina Fermions. So he introduced 2 kinds of Marina Fermions in this problem. One is a localized Marina Fermion, which sits on the bonds, and an itinerant Marina Fermions, which kind of moves around from one bond to the other. And by introducing these 2 kinds of Marina Fermions, he was able to rewrite this entire Hamiltonian just in the basis of Marina Fermions. And as soon as you do that, you basically automatically get that you can rewrite the excitations. You can write the whole physics just with Marina Fermions. What are Marina Fermions? Marina Fermions are basically their own antiparticles. So you can basically take 2 Marina Fermions. You can create it just from vacuum. If you give the vacuum some energy, it annihilates back to produce some energy. And they only annihilate and create back into each other, which means that they don't quite get scattered by anything else around it. So they already have this kind of DNA of protection kind of built into the way they're constructed. And so basically and that's what he was really in search for. You basically get all the excitations which look like Marina Fermions. In fact, he showed that you get 2 different kind of excitations in this system. One is basically this itinerant Marina Fermions, which kind of Marina Fermions going all over the place. And then the other is vortex anti-vortex. To think of how these really look, so you have these dimers forming and unforming at these various bonds. You get 2 different kinds of excitations. One is you get loop-like excitations, where the bonds basically break and unbreak in loops. So they form these loops. Now you can have a loop which goes clockwise or a loop which can go anti-clockwise. So you can get 2 different kinds of loops. So those are your, that's what gives your Z2 symmetry. That's like your upspin and downspin, if you would like. You get 2 different kinds of loops. And when you break a loop, you basically get 2 ends of that loop. And in that 2 ends, you basically get this itinerant Marina Fermions, which can go from all over the place. So closed loops basically gives you these fluxes or bosons. And when you can cut a loop, if you cut a loop, what you get is this, at the end of the loops, you get a pair of Marina Fermions. So every time you cut a loop, you get a pair of Marina Fermions. So the spectrum basically looks gapped, and that's why it's called the 2-flux gap, because you always get these Marina fermions in pairs. And this obeys the area law, and the entanglement entropy obeys the area law here. Anyways, what he was also able to show is that depending on how anisotropic these interactions are, you can construct the entire phase diagram. And if these interactions are completely anisotropic, then you would basically get a gapped phase, which conforms to basically the abelian ground state, which is conforms to the toric code model. But if you are right in the middle, which is when jxx will be equal to jyy is equal to jzz, you get this gapless phase. So basically, if you look at the excitation spectrum here, it basically is gapless at the Dirac point. And if it is gapless at the Dirac point, this is how the spectrum looks: momentum, and this is energy. It looks gapless at the Dirac point. And now, if you apply a small magnetic field, what this magnetic field does is that it kind of gaps this Dirac point out, and you get a new Zeeman splitting right at this Dirac point. And this is the non-abelian state that we are in search for. So what happens right here, as soon as you apply a magnetic field, is that you get this gapped states at the Dirac point. And in this state, you basically get bulk gap bosons, you get bulk gapped emergent Marina fermions, but you also get bulk gapped Ising non-abelian anions in this state. So you basically get four super selection sectors here. And then one is the bosons, which are this normal phase. You get some emergent Marina fermions, you get this Ising non-abelian anions, and you also get the half quantized chiral Marina fermions, which is a typical signature of these states. And what are these edge modes? These edge modes basically reside below the gap. And as you know, that if you get a state which has a non-zero Chern number, which this state is, and I'm not going into detail of what exactly is that, but if you have a topological system, in a topological system, you can define a winding number or a Chern number. Since this is a topological state, you get a non-zero Chern number. And if you get a non-zero Chern number, if you apply a magnetic field, what you will get is that you will get counter-propagating edge modes below the gap. So your bulk will be gapped, but your edges will be ungapped. And you remember that's how we showed that you get this protected edge states. This is exactly those protected edge states, but now in 2D instead of in 1D, and that's what you will get. But what you get is that you will basically get a Chern number, which will depend on the field direction, and you will get these edge modes. And these edge modes, if you can see this edge modes, that is actually a direct signature that you might actually have this non-abelianizing anions. So that's what we are in search for. And you can get to these states by doing a fractional quantum Hall measurement. So if you have a bulk gap where you basically have local states because of all the states are gapped out, you will still get a gapless chiral edge mode in the system, which is a signature that you can see in fractional quantum Hall effect. But this brings us to what is the experimental signature of all of these that I'm telling you right now. I mean, it's fine in theory, but we need to really go and see them. How do we do that? As it turns out that the experimental signatures of these loops and fluxes and also the Saiter and Marina fermions can be exactly calculated because it's an exactly solved system. You can do a quantum Monte Carlo. And both for the ferromagnetic Kitaev interaction and for the antiferromagnetic Kitaev interaction, you can figure it out. And you can figure out how the spectrum looks as a function of omega and q. And these are exactly calculated out for all scenarios, also as a function of temperature. So if you can really make a material in your lab, and then you can go and do this neutron scattering measurement or NMR or Raman measurement, you can actually try and see if you can see this phenomena, both quantum Hall effect and these states, then you know that you are there. You can see this phenomena. So that's what are the experimental signatures are. So which leads us to what are the material platforms where we see this. So as it turns out that there are several material platforms where you see this phenomena. And to get to those material platforms, there is this famous paper by George Jackley and Ginia Kaliolin back in 2009, where they showed that in order to get to these Kitab states, you have to satisfy a few conditions. What are those conditions? First is that you have to have a honeycomb type state, or this Y motifs as we talked about. Secondly, you have to have a low spin half state, and you have to have a strong cubic crystal field and strong spin orbit coupling so that you get to a effective J half ground state, which you get in these kind of ions. Thirdly, what happens is that if you have a strong spin orbit coupling, what happens is that if you have a strong cubic crystal field, you see that, let's say that this is the cation and these are the anions. If you have an octahedral cage, if you have the cation surrounded by an octahedral cage of anions, what you find is that this cation anion forms a square. Well, this is a 3D model, so this doesn't look like a square, but this is really a 3D square which faces kind of 3 different directions. And as it turns out that because of good enough Kanamori rules, all the Heisenberg interactions cancel out. Only interaction which survives is Ising interactions which come out of that square. So if you have the plane of the square, the only interaction which survives is the interaction which comes out of that plane of that square. So now you see that this square, the purple square, the green square, and the yellow square, all these 3 squares face 3 different directions in space. What that means is that you get 3 different Ising interactions on this ion in space, and that's exactly what your Kitab model is. That's how you get to the Kitab spin liquid ground state. Sorry. So there are several material platforms where you can actually get this phenomena, and not going into the detail, people tried to make these materials for a long time. I'll tell you something, that even though all these materials are made, none of this material is a real quantum spin liquid. You spend 2 years, a graduate student or a postdoc spends 2 years to make a material in the lab, and then you make the material after so much effort, you go and start measuring it, you see that it has ordered into some kind of a ground state, long-range ordered ground state. You don't get a spin liquid. And that's how nature behaves. Nature really wants symmetry. It wants to order up in some way. It doesn't like that disorder always. So that brings us to the question that, okay, fine, it disorders, but does all the spin disorder? Can we still get some signatures of quantum spin liquid remnant, even if you have some of this order left in the system? And that is some of the questions that we started asking. And this is how we got to this material called alpha ruthenium trichloride, where we found that the frustration factor is actually almost a factor of 10, which means that if all the spins would have ordered, it should have had a Néel temperature of almost 100 Kelvin, but it has a Néel temperature of 10 Kelvin. So there is a lot of spins which are basically disordered, and there is probably a some kind of spin liquid behavior which is going on there. So we started looking at these materials, and people have also started looking at sodium iridate, and they found that in sodium iridate you get this bond-dependent interactions as we talked about. And for those who are interested, they can look at this Nature Physics paper. Today we will be talking about alpha ruthenium trichloride, where some of my own work actually led to the idea that this is indeed in the quantum spin liquid state, or very close to the quantum spin liquid state. What we showed in this material is that if you look at the energy transfer as a function of momentum, you get a mode M2, which you cannot really kill. Even if you increase temperature over the Néel temperature, it kind of sustains to very high temperature. It's kind of protected. And if you look at the pure Kitaev interactions and how the spectrum of that would look, we were able to propose that, look, this mode M2 basically has the same kind of features what you should expect from an M2 mode that can come from Kitaev interactions. And that was really the Nature Materials paper that we published in 2016. We proposed that, look, it has a Kitaev interaction energy scale between 5.5 and 16 milli-electron volts. And the excitations match Kitaev's exact solution. It is not exactly a spin liquid, but it is very, 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 very close. So if you look at the phase diagram, at low energies and low temperatures, you basically get remnants of antiferromagnetic state, but it is very close to a Kitab spin liquid state, as if you can just take this line and move it a little bit, and you will go right into the Kitab spin liquid state. But lo and behold, at higher temperatures and at higher energies, you still get a part of the quantum critical fan. You get access to some of the quantum critical states that you would get from a quantum spin liquid. It took us a long time to make this material. In fact, it was me who spent with another scientist days and nights in the lab to really make the material that the pure ruthenium trichloride, which some of our scientists was able to grow into a very nice single crystal. So starting with pure materials is important. We did scanning tunneling spectroscopy measurement, which showed that this material has extremely strong spin orbit coupling, which is one of the prerequisites. And this material is also a very nice Mott insulator, which also shows that the spins are really static, but they have a freedom of motion. This material is air stable, which is very nice. And you can do STEM measurements, and you can take Scotch tape and exfoliate this material very nicely, and you can make monolayers. In fact, we had made monolayers and bilayers myself in my lab. One of my graduate students is working on this right now. Kiran my Dikshit is working on this right now. And we can make heterostructures and devices out of this material. So now we are getting into the realm where we can make quantum electronics out of a spin-based material, from a frustrated spin-based material. So that's a very exciting new territory to be in, because it's completely unexplored. So, but let's go back to the neutron scattering results. So this is some of the neutron scattering results that we published. What we find is that if you look at the intensity as a function of energy at the gamma point, you do start to get, so at low energies and low temperatures, you get these sharp modes as a function of energy, and you get that sitting on top of a broad continuum of scattering. And these are the broad modes that we are in search for. And as you see that this doesn't look like a paramagnet. If this was a paramagnet, this would have been just a Lorentzian centered at 0. That's not what you get. What you get looks different. It almost seems that you have an emergent incipient gap. And so you can map the states to what the Kitab solution looks like. And as it turns out, that the higher energy spectrum basically looks like what you should expect from Kitab's exact solution. So this is Kitab's exact solution. This is the spectrum that people have measured in neutron scattering, including some of my own papers. So, and as you see that it matches very nicely. But the low energy spectrum doesn't quite match up so well. We see the Star of David type pattern, and what the pure Kitab state looks like is something like much more isotropic. And that's because you have renormalizations coming from this long range order. So you know that you are very close to the Kitab state, but you're not quite there. But still, you are very close to the Kitab state. So that's already great. I mean, that's already quite an achievement. So that is what really excited the community. But the goal was that, we are very close to the Kitab state. Can we nudge this material a little bit to make it go to the pure Kitab state? And then there are several experiments which happened. There are probably now 200 papers which came out after our discovery on this, and which included terahertz measurement, Raman measurements, resonant inelastic X-ray measurements, all of which confirm that you see these phenomena, you see this itinerant, you see this broad continuum of scattering, and this broad continuum of scattering actually comes from Marina Fermions, this itinerant Marina Fermions that we talked about. But how to nudge this material into a pure Kitab state? What you can do is that you can apply a magnetic field. So let's look at the field-dependent phase diagram. So this is temperature and this is field. What you can see is that this is the field and temperature-dependent phase diagram that we measured. Is that at low fields you have this zigzag antiferromagnetic state, which goes into a gapless state to a quantum spin liquid state, is what we figured out. How did we figure that out? We did neutron scattering measurements, and this is energy versus momentum. What we found out that at low energies and low temperatures and at low fields, you see this kind of an oscillating pattern of intensity. So red is high intensity, black is low intensity. This red region comes from elastic scattering. So let's forget about that. What we are more interested in is this cloud-like features that we see here. So this, if you squint your eyes, you can see what the scattering looks like. It kind of looks like this zigzag kind of a pattern. And those are the magnons, but it is also sitting on a back of spin-ons that we also see, which is this cloud-like spectrum that we see. That's at low temperatures and low fields. It goes through a gapless phase. And then finally, at 8 Tesla, what happens is that all the magnons disappear. You have no Lagrange order left in the system. You get to a pure spin liquid ground state. And what really happens is that we start to see a tiny gap kind of coming up right there, right at the gamma point. Now, you can't but beg to answer that question, that is that really the gap we are looking for here? Wow, is that really the gap? And should we see these edge modes? So when we published this result, there was a group in Japan which went ahead and looked at the quantum Hall effect. And lo and behold, what they found is that you indeed see a very robust half quantized fractional quantum Hall plateau in thermal transport and thermal Hall effect in this material right at this 8 Tesla state. So what they did was that they actually attached thermometers on a piece of sample in the Hall configuration, and they used a kind of measurement called the Righi-Leduc measurement. And it's a very difficult measurement, by the way, especially in a high field. But when you do that, the Hall conductivity basically has a half quantized plateau, corresponds to a value of half here. And this is a robust state that they saw, which is the robust state where exactly we saw this quantum spin liquid ground state with this gap, probably this gap state right here. And that was great. And not only that, there is this PRL paper by Bruce Normand, and which showed that if you move the field in different directions, you should get a different Chern number. So at different directions of the field, in some directions, you would not get this plateau, while in other directions, you will get the plateau, but the plateau will be at a value of -half instead of half, corresponding to a Chern number of -1 or +1. And they were able to exactly show that as well. So there was another paper, which was the Okoi paper, which was published in Science in 2021, which showed that this really complies with this picture that we see here, is that if you apply the field in different directions in the sample, you really have a control over the Chern number of the material. So there is a lot of results which are out there, and there is some sample-to-sample variation, which we need to be aware of. So the Kasahara Nature paper showed that the thermal Hall effect happens at around 8 Tesla, while the Yokoi paper says that it happens between 11 and 12 Tesla. Then there is this Bruin archive paper, which I think will come up in Nature Physics sometime, showed that it happens between 10 and 14 Tesla, quite high field. And then there is this paper from the Princeton group, in which I am also a co-author, where we showed that at low fields, you basically get this quantum Shubnikov-de Haas type oscillations in the longitudinal conductivity kxx as a function of field. And that's actually a very, 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 very weird phenomenon, because in order to have Shubnikov-de Haas, you need to have a metallic state, but this is an insulator. So how can you have that here? And this probably begs new understanding, but it probably points to a spin-on Fermi surface. But again, if you have a gapped ground state, how can you get a spin-on Fermi surface? We don't know the answer to that. So new theory is required here. And the fact that we really have a gap there is being shown by, as it turns out, when I joined Purdue University, right now I have 6 graduate students. All of the 6 graduate students come from 6 different countries. But my first graduate student was Kiran Dixit. So she's from India, from IIT Guwahati, joined me. And she did some excellent measurements on looking at what happens as a function of neutrons in field. So this is energy versus the momentum. And what she found is that she used a high-spec instrument with a 14 Tesla split coil magnet. And what she found is that these are the excitation spectrum that you should look at. Don't look at the yellow. Look at this cloudy feature. And this cloudy feature starts to have a gap right at the gamma point. That's the gap that you start to see. And that complies with this picture. And not only that, what we would be able to show is that there is indeed an energy gap beyond the error bars at all points of time, roughly half a MeV, so 5 Kelvin gap. So 5 Kelvin is a big gap, actually, I would have to say. So anyway, so that's where everything is right now. One question that is faced by the community, and a lot of research is going on, is that why does the system order? If you just had these Kitaev interactions, then the system should have been in a quantum spin liquid state. But in a real material, you really can't just have this one interaction. You basically have some second order Heisenberg interactions, second order, all kinds of parasitic interactions, gamma interactions. And when you have that, you basically can get many kinds of long range ordered ground states. And then this begs the question, is proximate spin liquid good enough for this topological physics? Do we still have Marianas which are non-abelian, or this some kind of renormalized Marianas that we are looking at? And these are some of the burning questions for the community right now that I think the community needs to address, is that since it's very difficult to get to a pure spin liquid ground state, we can only get to approximate state. How good is the approximate state? Is it good enough? Can we say for sure this is good enough so that we can go and start making devices? And speaking of devices, so this is also big research which is going on right now, and this is in collaboration with the Caltech group and with Microsoft Station Q, where what we are trying to see is that can we take these non-abelian anions, or the signature that we see, these edge modes, and we can start to braid them and make go towards qubits, go towards topologically protected qubits, topologically protected by this 5 Kelvin gap that we just figured out. And so there are new kinds of devices that are getting proposed. For example, these point contact, quantum point contact interferometers is what people have been thinking of quite a bit. And these are the papers for those who are interested. And so this is also another very exciting direction, which did not exist even 2 years ago. But now we are starting to think of this type of magnetic tunnel junction type devices, which if we can get to would be a great opportunity. And for example, our own group, along with help from people at the electrical engineering department at Purdue, we are doing an experiment where we took this quantum spin liquid material and put that on platinum and made into a Hall bar sample. And Hall bar and platinum has spin Hall magnetoresistance, which can bounce off this quantum spin liquid states, and you can read that off, those states off. And not going into the details, you can actually see that temperature scale in these measurements as well, which is very nice. Now you have a transport way of measuring these spin liquid states. So I'm not going into too much details of some of the other research that we are doing in our group. Some of the other research that we are doing relates to looking at these states using a real quantum computer like IBM, like Fujitsu, like D-Wave. There is some very exciting research which is going on, and I can talk about that in more detail probably in another talk. But just to showcase some quick results, which came up from our group in collaboration with Oak Ridge National Lab, is that, for example, in this Chassis-Sunderland Hamiltonian, this is the proposed phase diagram published in the PRL paper. We use the D-Wave quantum computer to basically find the phase diagram out, and this is the D-Wave result. It exactly matches the phase diagram that we see for the Ising Chassis-Sunderland Hamiltonian, and we can also look at the critical states and the critical phenomena in these systems. But we are also using the IBM quantum computers and Honeywell quantum computers. So postdoc Zoe Holmes and my PhD student Nora Norhan is working with IBM right now to look at these states and how to beat the noise floor in these quantum computers in order to get to start to see some of the signatures of this exotic states. We are far off, really far off, but we are starting to think about it. So that is the end of my talk, and thank you for letting me go a little longer, but I will put up the conclusion slide here with the hope that this spawns a completely new kind of quantum electronics based on magnetic materials in the future. Thank you.
Thank you, sir. A very nice talk. We all are mesmerized with your work which you have done. I extend my hearty thanks to you, sir, for this informative talk and explaining very elaborately the topic quantum spin liquids, novel platforms for emergent quasi-particles. So we were able to understand various states of spin, the quantum spin liquids, the phenomena of spin-on propagation, the concept of magnetic frustration in triangular matrix, honeycomb matrix. You also explained the concept of Marina Fermions, bosons, and anyons. The tools by which we can measure these spin dynamics, really very difficult to arrange all those things. And you explained everything in a very interesting manner. Thank you, sir. Now for the question and answer session, I would like to request Dr. Ashwini to take over. Over to you, Ashwini, sir.
Thank you, ma'am. Thank you for providing this opportunity. So all of you are requested to type your questions in chat box so that I can read it out for your convenience. And let me start with the first question, which is related to the Aditya Sagar Shukla has asked this question, that how quantum spin liquids will help in development of quantum bits or qubits for quantum computation.
Well, it's a very loaded question. You understand that. There is a whole cohort of people who are working day and night right now in order to understand how exactly this can happen. And I'll tell you why this is so difficult, because unlike in something like topological insulators or unlike in a Marina spin chain, here the emergent quasi-particles appear in one single matrix, which means that you cannot have separate spin liquid islands, and you cannot kind of join them using quantum point contacts in order to make this quantum point interferometers that we just showed. So that was the slide that I showed here. You cannot actually you always have to have one single quantum spin liquid matrix all the time, and which means that you cannot really construct like islands of different qubits. And then it becomes a very difficult mathematical problem and also a real topological problem of how do you do this braiding phenomena, really, between all these edge modes. And so that's a challenge, and that's a challenge which is taken up, thankfully, by quite a few theorists, and we invite more theorists to help us with that. Basically, one of these, and this is not a paper in which I am a co-author, by the way. This is this paper by Liu and Burch and Jason Alicia, this archive paper which just came out, where they have shown one such scheme in which you can get to a quantum point contact where you have a trivial phase which is made by a magnetic tunnel junction, where you don't even go to braiding here. You don't even do a quantum computation. You just show that braiding is possible using this quantum point contact. So the next state would be to have maybe many such these quantum point contacts, and then you can start to kind of braid them and get to the quantum computation. But as you see that we are not there yet, and the theory for that is not developed yet. So that's an opportunity.
Ashwini, sir, you are muted.
Sorry, ma'am. Let me read out. Next question is asked by a student. that in Pauli exclusion principle, can two spin half particles have same quantum number with different masses?
Let me make sure I understand that question carefully. So,
he is asking that with different masses, can four quantum numbers will be same if the electron mass is different? I mean, two electrons with two particles with different masses.
So, if you're talking about effective masses, and if effective masses means, and if I understand that question correctly, you are not just talking about that the electrons themselves have different masses. What you're really talking about is that you basically make this electronic quasi-particle states, which basically have different masses, which means that they have different gaps and different energy states. If you have different energy states and masses, you mean that you get a massive gap opening up, a mass gap opening up in the spectrum, then there are two things which can happen. I mean, as long as these two electrons are in two very different energy levels, then yes, they are effectively in two different quantum numbers, if you can define it that way. But as you see that in these degenerate states, it's very difficult to say that this electron is in this state, that electron is in this state. All the electrons are in all the states at the same time. So from that standpoint, yes, the electrons, as long as they're in different locations at different points in time, yes, I don't see how they can have the same quantum number. So they are not separated in momentum space, in momentum energy space, but they can be separated in the real space, in the XYZ space. Then yes, it is completely possible. Now, if you consider a situation when both in momentum and in real and reciprocal space, the electrons are at the same point in both space and time and in momentum and energy, then I think, of course, that's not possible.
Okay. Any other question, please? If you have any other queries.
One of our senior faculty, Partha sir, has raised his hand. Partha sir, you can ask the question.
Dr. Arnab, hello, am I audible?
Yes.
Hello.
You are. Yes.
Dr. Arnab, I would like to know, like in a system where you have vortex formation, right? And in the vortex, you search for a vortex becomes non-abelian aliens with Marina zero mode, right? Now, what exactly is the mechanism by which a vortex becomes non-abelian aliens with Marina zero mode? I would like you to shed light on that. Am I clear?
Right. So what you are asking, let me understand, and I will make a confession right in the beginning that I am not a theorist. I am an experimentalist, but I will try to see if I can answer that question. So, what happens is that when you don't apply a field in this kind of a material, let's say, and this is an universal statement I'm making. If you don't apply a field, then you basically have this vortex anti-vortex states, right?
Yeah. Yeah.
So, and these vortex and anti-vortex states have the same energy.
Okay.
Because it takes the same amount of energy to make a state in the positive chiral fashion as in the negative chiral fashion, or the anti-clockwise or clockwise, if you would like. They have the same energy, but and the other thing that you see is that you can act. So these vortices are just not these spins, these dimers here breaking. These loops or these loop operators can be even bigger. They can be like this. They can be much bigger. They can be even bigger, so on and so forth. They can have various sizes. But one thing is certain, that these loops basically have the same energy at the end of the day. When you apply a field, what is field doing is that it is like a perturbation. And if you think of just a first order perturbation theory, what it does is that it breaks the symmetry in between these two positive chiral and negative chiral, this anti-clockwise and clockwise states, and it creates a gap in between them. It gaps the states out. And when you gap the states out, what you have is something very interesting. So you basically get the ends, you have now created this tiny gap between this positive and the negative states. And the other thing which has happened is that the lowest levels of the state is like a Van Hoff singularity. That part behaves like a boson. So the ends, so if this is the dispersion, the ends of this, and you have created a gap right now. This ends of the gap basically behaves like a boson, but while the upper part is basically the Zeitner and Marina Fermions. So you have basically created a state when you have gapped this whole system out from just being like bosons, which are these flux and anti-flux pairs, into a state which has both some flavor of a boson and a flavor of a fermion at the same time. And that kind of is basically like the super selection sector of anyons, which are neither fermions nor bosons. So that creation of that antisymmetry between the between the plus and the minus chiral states are actually extremely important, because that's when you get this emergent bosonic character in this otherwise fermionic spectrum, and that's what gives rise to this effective anyons.
So may I suggest, like, suppose you have something which probably you are working on, or probably you are not. So say Bi2212, a high TC superconductor. You anyway, so it has coexistent pseudo gap state and superconducting state, right?
Yes. Yes.
Now, in the coexisting pseudo gap state and superconducting state, supposing I assume pseudo gap state to be something like a chiral d-density wave state as floated by Shankar Das Sharma. The idea was floated by Shankar Das Sharma. Okay. And we have the coexistent pseudo gap and superconducting d-densities wave superconducting state. Supposing I now apply the field that you are talking about, the time reversal symmetry breaking Zeeman field. Okay. Will I get vortex-like structure, non-abelian, say, aliens with Marana modes at the end? Is it possible? All thinking is hypothetical. I'm thinking of it.
So, of course, an exact calculation will need to be performed. But absent that exact calculation, so what the scenario which you're describing is...
No, you think that all the recipe needed to see Maranas are there, and aren't they? So what do you see? Forget exact calculation. What is your guess? Would there be Marana's zero mode?
So for the scenario where you have basically a topological insulator which is coexistent on a superconducting pseudo-gap state, you basically get this very new kind of state called the topological superconductor, which many people are searching for right now, because the conjecture is that you would get Marana bound states there. But unlike here in a quantum spin liquid, where you don't get Marana zero modes necessarily, there you get there you get basically this Marina zero modes. The difference is that those are basically real space zero modes that you get, that you can really do braiding on much more easily, actually. So, so yes, if you can get a topological superconductor, which is like a TI mated with a pseudogap state, if that mating is really there, which means that they coexist in the same space in the reciprocal lattice, then the answer would be yes. That's the conjecture.
Yes.
And I think that follows from the Protein hypothesis.
In fact, we have been able to show that BI2212, it has strong SOC. So it turns into a QSH, quantum spin Hall insulator, which is basically a topological insulator. Isn't so? Isn't it so? So with that background, I don't know. I've not been able to do the whole calculation. I'm just seeking your opinion whether it could be possible.
Yes. So has anybody? So is this experimental or theoretical?
No, mine is totally theoretical work.
Okay.
Ours is theoretical work.
So, so I think that the calculation which might need to be done, and again, I am not the biggest expert on it. Maybe somebody like Liang Fu or Charles Kane would be, or somebody in that. But what I think is that as long as you can show that you can get a gap in the TI structure at the direct point, and secondly, the pseudo gap in the momentum space exists at the same point, so they coexist. And then I think we are in business.
Okay.
That's my.
Thank you. Thank
that's
you
my
very
feeling,
much.
that they have to be in the same place in the momentum space.
Right. Thank you. Thank you very much.
So let me move for the next question, and that is asked by Dr. Amit Chaudhary, sir. And the question is, what are the possibilities of existence of ferroelectricity in quantum liquids, as it is in the case of quantum nematics?
There are already a couple of papers, which I think I can probably, if he can email me, I can email him back. A couple of papers. Now, those are not by our group, but there is a group in Germany, and then there is a group in Japan who have looked into the possibility of multiferricity in quantum spin liquids. It is a possibility. Of course, you would need a strong spin charge interaction, and as we have seen that in these materials, in order to see the quantum Hall effect that people have seen, you need to have a strong spin charge interaction and a strong spin phonon coupling. And when you have that, these materials, especially if you have some kind of a non-centrosymmetricity associated with this material, you can actually get to a effective ferroelectric state. And there are some groups who have actually tried to measure that. And we welcome some more research on that side, because maybe if you can show that we have ferroelectricity, then in interrogating these kind of magnetic quantum materials using electricity will become a lot easier.
Okay, so let me move for the next question that is asked by some student Aryan Khare. And he want to ask that how to distinguish quantum spin liquid from a classical one at finite temperature? I mean, is there anything like classical spin lattice also?
Yes. So there is a paper that we published in PRB. The first author is Anjana Samarakun, and I am the second author, where we looked at the results from quantum Monte Carlo versus classical Monte Carlo. And what we figured out is that some of the spectrum looks very different for the classical spin liquid. You can also get a classical spin liquid where basically the higher order Heisenberg terms are basically all neglected. So you are only doing a simple Landau-Langevin equation that you are solving in a semi-classical form. And when you do that, you can get to a spin liquid state, but that's classical spin liquid does not give you the gap at the gamma point. There is no two flux gap. So basically what you get is just a simple continuum which is peaked at zero energy, and it more or less, the zero energy spectrum looks like a paramagnet, and then you basically get another mode which kind of hangs right at the Ising point, and that's like more like a bosonic mode, which is much sharper. It doesn't look like this broad energy states, this fermionic like energy states that we see. So yes, you can get a classical spin liquid state, and we have contrasted how the important point is that there also you see two modes, but the two modes do not look the same as that in the quantum case.
Okay, Disha Wadwan want to ask that could you please elaborate what is meant by the film being air stable?
What it means is that over a period of time of, let's say, 24 hours, if you just keep the film out in the air, it doesn't lose any of its ligands, getting replaced by either water, humidity, OH group from the atmosphere, or the oxygen. So if, let's say that you have chromium trichloride or some material like that, or molybdenum trichloride, what happens is that if you smell this material in the powder form, it will smell just like bleaching powder. Why? Because the material is just giving off these chlorines, and oxygen is coming and sitting in its place, or OH group is coming and sitting in its place. Somehow it turns out that when you make a single crystal from these materials, the system really likes to be in that single crystalline state. It becomes very stable, as opposed to if it's in the amorphous state. And then it doesn't lose this chlorine so easily, which means that you can keep that in open air, even a single monolayer in open air, for quite some time, and it will not degrade, and it will not bleach.
Poonam Jam ma'am want to ask that is it also possible to include time-dependent magnetic field in place of static magnetic field?
I am glad that you asked that question, because what you're asking is whether we can do flow dynamics in these materials.
Exactly.
Quite a few groups have been thinking of doing flow dynamics in these materials, not as a function of magnetic field, but as a function of light. You shine light in the system, and it is possible to, of course, modulate light intensity much easier than the magnetic field intensity. The reason it is very difficult to kind of do a flow dynamics with magnetic field is because of something called eddy currents. So as soon as you change the magnetic field very fast, you basically produce, because of Lenz's law, you produce this eddy currents, and this eddy current heats up your sample a lot. And if you have heated up your sample, you just go to the paramagnetic state. So that's why it's so difficult. But so it's you can do this experiment if it's a very tiny magnetic field which you can kind of oscillate. But people have been trying to do this flow trying to design flow type measurements using light instead of magnetic field.
Okay, so since no more questions, so let me conclude this session by thanking you, sir, for nicely giving the answer, all the answers to the questions. Over to you, Monica ma'am.
Thank you, Ashwini sir. Now I would like to request our IQAC coordinator and respected faculty member of Physics Department, Dr. Aditya Saxena sir, to give vote of thanks. Over to you, sir. Aditya sir, am I audible? Yeah, sir. Oh.
You are not audible, sir, actually. Aditya sir, you are not audible, so unmute yourself, please.
I'm sorry, sir. I'll just allow you.
Yeah, so thank you so much, Monica. And it is my honor and privilege to propose this vote of thanks today for this very, very intellectually stimulating and a very informative lecture on quantum spin liquids, novel platforms for emergent quasi particles under our international lecture series on recent advances in physics. And I would like to begin by extending a very heartfelt gratitude to our keynote and very distinguished speaker, Dr. Arna Banerjee, from the Department of Physics and Astronomy, Purdue University, West Lafayette, and visiting scientist, Quantum Computing Institute, Oak Ridge National Laboratory. I would also take this opportunity to express my sincere gratitude to our very dynamic and helpful principal, Professor Rajiv Agrawal, who has constantly provided us guidance and helped us towards arranging and organizing such activities of academic nature, and who has also always supported us on all such endeavors. I would also like to take this opportunity to thank our Vice Principal, Professor Kamal Kumar Gupta, who, despite his extremely busy schedule, is always there to encourage us, to motivate us, to guide us, and is always there to extend a helping hand to all such activities that we are organizing. I would also like to express my sincere thanks to our teacher in charge, Dr. Kakuli Bera, for organizing this international lecture series on recent advances in physics, and who has actually conceptualized and implemented this idea. Then my thanks are also due to all our faculty members of the physics department, especially our senior faculty members, Dr. U.P. Tyagi sir, Madam Manjurani, Dr. Pankaj Singh, who is also our Physics Society convener, and who has also been actively involved in the organizing of this event, and Mr. Ajay Pratap Singh Gehlot, and also all our younger colleagues who have worked tirelessly day and night to ensure that this event becomes a huge success. My sincere thanks to our esteemed senior colleague, Dr. Partha Goswami, for joining us for this lecture, and to all our senior colleagues from other departments in Deshbandhu College, and to all the other faculty members from the other colleges of University of Delhi. And my biggest thank is to all the students who have today joined us for this lecture and who've actually ensured that not only this lecture becomes successful, but the real purpose of this lecture is achieved, that we wanted that our students should get exposed to the latest research that is happening in the field of physics. So by the fact that they've not only joined, but actively participated in this lecture, and they followed this lecture, has only reiterated that this effort that we were making has succeeded. And finally, I would like to thank our technical team, Dr. Monica Bajaj, Dr. Monica Sharma, Dr. Brijmohan, and Dr. Ashwini Kumar for managing the background work. And finally, my sincere thanks also to our DBT Star College Scheme Coordinator, Dr. Indrakant Singh, whose constant support has been there for our department and who has also supported us in establishing a nanophysics lab in our department. So my thanks to him. And thank you everyone for joining us for this session. And now back to you, Monica. Thank you.
Thank you, sir. Again, I want to thank all of you, and especially you, sir, that you take your time and give us a very informative lecture. Thanks. The session can be closed now. Thank you, everyone.
Thank you, and it has been my honor.